everybody. Today we're going to be going over one of the kinetics questions. One thing I have found recently with the AP exam is that if you have a kinetics question, it is usually either half of one question or it's one little tiny question. And I'm not 100% sure if you're going to have a little tiny question on the exam this year. It seems unlikely. So I would expect if you do have kinetics stuff that it's going to be part of an integrated question. But in this case, it's mostly one little question from the 2019 exam. There are two questions, and that's why I'm saying this is because we got two little baby questions that relate to your different FRQs. So this is 2019 number 6, and we're going to start off. There is a lot of stuff here. It says nitrogen dioxide is produced as a byproduct of the combustion of fossil fuels in an internal combustion engine. At elevated temperatures, it decomposes according to the equation below, and then they give you the balanced equation. The concentration of a sample of NO2 is monitored as it decomposes and is recorded on the graph directly below. Now, when I look at this problem, I instantaneously know without reading any text that this is going to be a kinetics problem. And the reason why I know that is because I've got 3 graphs of different things, and one of them is a straight line, and that is how I'm going to know. Watch with this, though, because I'll show you a tricky thing that the College Board is doing here. Let me take this sheet of paper out, sorry. All right, so it says, explain how the graphs indicate that the reaction is second order. So you look at this and you're like, hey, they told me it's second order, but I should have known that already. So if you look at the graphs, we have a graph of concentration versus time, a graph of 1 over concentration versus time, and a graph of the natural log versus time. And so in your head, you say to yourself, well, you know what? This should be 0, 1, and second order. However, they put them in there, I think, intentionally mixed up to screw you up. So this is 0 order. Natural log is first order, and 1 over is second order. I would definitely have this on your sheet. So what you need to do is for A, it says explain how the graphs indicate that the reaction is second order. The reaction is second order because a graph of 1 over concentration of NO2 is linear. And that's literally all you have to write. Resist the urge to do more. That is all you need to do. That's it. So stop writing a novel. Okay, sorry about that. I got a little worked up. Okay, so for B, it says write the rate law for the decomposition of NO2. They told you it was second order. So my rate law is going to be rate equals K times the concentration of NO2 squared. Boom. Done. Easy point. Okay. C says consider 2 possible mechanisms for the decomposition reaction. For part 1, it says, is the rate law described by mechanism 1 shown below consistent with the rate law you wrote in part B? Justify your answer. So this is where we come back to mechanisms and remembering that the number of each element that you have or their coefficient is the power when we talk about a mechanism step. We call these elementary steps, and so in an elementary step, the only time this works is that if there are 2 of these, it becomes a power here. In a balanced equation overall, that is not the case, but we do need to double check. So in this case, we are going to look at the slow step. So the rate determining step is the slow step, the one that makes it controlled, and so we look at that. So if we look here, if I would determine the rate law for the mechanism, I would put rate equals K times the concentration of NO2 times the concentration of NO2, which equals K times NO2 squared. So if we look, basically, based on this mechanism, the rate that comes from the mechanism, the rate law, matches the experimental amount. So I'm going to do some sort of work to represent that the rate law from the mechanism is this, and then I'm going to say rate law from mechanism is consistent with experiment. Data. I guess I'm writing a little short here. The rate law from the mechanism is consistent with experimental data. And we should be good to go. So all we need to talk about is how this rate law here, coming from the elementary steps, matches up with what the data shows. Okay? They give you kind of a lot of text, but I think that if you just show the work for figuring out the rate law from the slow step, I think that you should be fine. Okay? For part 2, this one's a little harder, and this is a slow second step, and that one is a little more complicated, and we kind of cruised over it in class, so I'm going to try to spend a little bit more time on it, and we'll talk about it a little bit more. So it says, is the rate law described by mechanism 2 consistent with the rate law you wrote in part B? So what we're looking for now is we still want the rate to be rate equals K times NO2 squared. But if we look here, we always have to pay attention to the slow step. So our slow step here is our rate determining step. Which means that in theory, if we wrote our rate law, it would be rate equals K times the concentration of N2O4. However, if you remember, N2O4 is made in the product of the first step, and then it's consumed in the reactant as in the second step. So that is what we call an intermediate. And intermediates don't show up in a rate law. So what we actually have to do is we have to do a substitution. And this is called a steady state approximation. You'll hear them use it sometimes. So the steady state approximation says that because this first reaction here is a fast equilibrium, which means that like lickety split, it goes into equilibrium. The rate that we get one is essentially the rate that we get the other. And if you remember equilibrium, the KEQ for the first step is what's always products over reactants. So it is going to be the concentration of N2O4 over the concentration of NO2 squared. Hopefully that makes sense to you. I'm just referring to step 1 here. This would be the KEQ for that one because it's coming to equilibrium quickly. So if I do a little bit of kind of like algebra magic, I can rearrange it so that NO2 squared disappears from the side of NO24, and I'm going to bring it to the opposite side. Okay, so these cancel out. So what I'm left with is a situation where the concentration of N2O4 is equal to an equilibrium constant times the concentration of NO2 squared. And what I can do is I can basically do a substitution where I take the N2O4's concentration with this sneaky substitution and plug it into this rate law. So what ends up happening is that the rate is equal to this K value. And yes, there is this like little extra KEQ value in there, but that gets kind of rolled into this KE value. So I've got the KEQ value. So K is equal to this KEQ times the concentration of NO2 squared. And so in this situation, like I said, these two K's kind of combine with each other. What'll end up happening is that essentially it's the same rate law. So if I substitute in the intermediate with my rate law, I do end up getting a rate law that's consistent with what the experiment shows. Okay, so if we look at this again, this substitution method allows me to say that yes, it is equal to NO2 squared. And so I would say, how am I going to word that? I think a lot of the math would kind of represent itself. So what I would say is by substituting out the intermediate N2O4 in the rate law. The mechanism does match up with experimental data. Okay, so this one's a little bit harder. I don't know if they're going to give you one of these on the test, but that is how it works. So if you have any questions, especially on this stuff, pop into a meet and we can get things cleared up.